Hello all and welcome back. So in this video, let us now continue our discussion and now let's see another way through which we can store our graph. Now in the last video, we discussed about edge list. We also understood what is the problem if we are storing our graph as an edge list, right? The O(n) square time complexity in finding out if there exists an edge between between any two nodes, right? So now let us learn about the adjacency list. Now this is something which you will see at many places being used as well. Edge list, I made sure that I help you implement and also teach you. But normally because of that complexity issue, it is not used majorly. So you will not find that in questions as well. But you should be aware that yeah, that's the most easy and straightforward way. Now let us move to adjacency list. Now, coming to adjacency list, what our mind or what our overall intuition is that, let's say I have a graph like this. So this is a node which is A, B, C, and D. Okay. So this is A. A is connected to, let's say this. We can take it as a undirected graph. That should also be fine. B, C, and D. A is also connected to this. Let's say there is a connection like this as well. Some connection like this as well. So D and B, right? Now, what our overall intuition here is that hey, instead of storing all the edges at a single in a single list, right? Why can't I just ask each and every vertex that hey, who all are you connected to? That's just the major mindset or the intuition. To just explain you this a lot intuitively, instead of finding that if you are, let's say, following a person or your friend on an Instagram, instead of going through all the connections which are stored in Instagram, why can't I just go to your profile? Something which you do as well, right? Why can't I just directly go to your profile and directly see who all are you following? In that, I will be able to just check if you are following the particular person or not, right? So let's say, for example, if you as a person you are following Kobe Bryant, who is a basketball player, or let's say Virat Kohli, a cricket player, or Ronaldo. So I can go to your profile, see all your followers, or see all who you are following, and then basically find out from there if you are following that particular person or not, instead of going through all the connections which are present in my Instagram. Okay, so all the following connections or information which is present. Now I hope you are able to understand the magnitude by which we have reduced this problem. Okay, so again I will just draw it out as well. Let's say we have something like this. For A, I will somehow ask A that hey, just store who all are you adjacent to. Now, I hope you remember from our discussion what are adjacent nodes, right? So who are connected to each other. A will thus make sure that it will store it in a list or something. It will store that hey, I am connected to B and C. So just by making sure we are storing like this, we can make this whole problem in O of n. We can actually make it in O of 1 as well. We can use a hash map or a dictionary instead of list. So I hope all of you remember we have implemented hash map from complete scratch, right? It gives you a O of 1 overall search and access. Okay. So yeah, that's the basic idea. For B again, what we are going to do, everyone? B will store whom all it's connected to. So it's going to be C and D. Now we can store it in a dictionary somehow. And not C and D, it's C, D, and A, right? C again can have something similar than D. Now here we are storing a adjacency list in a way. So that's the reason it is known as adjacency list way. Okay, and we can now of course code the same as well. But I hope you got the basic idea. Again, in worst case, if we are storing it as a list, then On is the time complexity for finding out. Now we are discussing with respect to this operation of finding out if two nodes are connected. Because again, that's a very basic operation which you will surely be doing in your graph. If let's say on Google Maps, if you can think, the source to destination, if two nodes are connected, that's the most basic operation which we do. Okay, cool everyone. So let us try to implement this now. What we have to do is let us just make a new file. Here I can make graph using adjacency list. Again, class graph adjacency list. So it is known as adjacency list as well, because we have the list of vertices and then they are storing it. It can be the dictionary or a list as well. Should be fine. Let us create a constructor. So self dot vertices, something like a list. Then self dot adjacency list. It's going to be a dictionary. Now, as we move forward, I will tell you how exactly are we going to store. So as we code, you will understand how exactly will we store inside this dictionary. Add vertex. Okay. Add vertex. I will be getting the information of vertex as well. Now see, if vertex not in self.v, what we have to do? Self.v.append. We can append whatever vertex you are sending me. And self.adjacency list. Here I am going to create a overall vertex as the key, and it will be having a dictionary here. Oh, sorry, it will be having a list here only. We can use again dictionary as well, but that should be fine. Let us use list as list only. Else, we can say directly print f vertex already exist. Now, one more reason we use, and I am specifically using list here, is that what happens in many languages like C++, Java. Java, I think, has map by default. C++ doesn't have anything. We have to import that, right? But an array or a list is always present in each and every language. Doesn't matter what language it is. It will surely be having the implementation of array or a list by default. Okay. So again, that is the reason it is very important. We have to make sure that we understand the concept, not just learn DSA through Python. DSA is a concept. We are using Python to do the same. Great. So now let us add an edge. So add edge. Again, self, source, destination, weight. Okay. Weight, let us make it 1 by default. And this time we will be making it undirected. So last time we did it a directed graph. This time we are going to make it undirected. So no arrows or anything are there. Right? Great. Again, if self in, sorry, not self, if source in self dot vertex and self destination in self dot vertex, then we have to do something. Self dot add self dot adjacency list of source, we have to append in this a tuple. Tuple is something like this: destination and weight. Okay. And because I have to make it bidirectional or undirected, what I have to do, pay attention everyone. So let's say this is my source and this is my destination. As of now, I have said that this particular adjacency list, it will be something like this. I have a source here. In this, I have a list where I am appending d comma 1. To make it a undirected graph, in d as well, I should append something like this, right? So now you can go either from d to s or s to d. So this operation and this both are done. Either you can draw the arrow or you can just leave the arrow as it is. That should be fine. Okay, great. So yeah, let us do that. Let me just remove this and copy it. So in the last, we didn't use it, but I hope now it should be clear how exactly this is. Destination, source. Great. So once this is done, and we can just write here, assuming undirected graph. Else, again, we can just print one or both vertices not found. So again, making sure that we are following very nice OOPS practices, each and every error very nicely visible to the end user. Next one, we can just print here display. We have the self. Okay. So again, here what we have to do, just like we displayed everything in our edge list, we have to do the same thing here. So let us do print. So first let us print the vertices. So for vertex in self.v, I should just print out the vertex. Okay, so that we are aware that all these are the vertices. Now comes where we have to print all the overall edge node and who all is it connected to. So let us make it like this: vertex and neighbor, or we can use the name as connected node as well in self dot adjacency list dot items. Now I hope all of you remember what exactly. I will just show you the structure as well here. Let us make this test.py. So pay attention everyone, what's happening here. I am making a dictionary something like this. So it's A, and in this A we are saying we have something like this B and a 1. Okay, then we have, let's say, B. For this B we again have something like this only, A and 1. So this is the structure. Okay, this is our structure. If I do print d dot items, so, 1 minute, d dot my bad, so self dot adjacency list dot items, we are getting this. Let us just run a loop. So for vertex and neighbor in d dot items. Now what we can do, everyone, pay attention. I can just print out this vertex, vertex and neighbors. So we will be able to see everything pretty nicely here. Where it is the invalid syntax, neighbor, my bad. Okay, what is it saying? Int f. We have closed this. Yeah. Great. So I hope you're able to see that for A, I'm getting all these vertices. For B, I'm able to see the same. So let us just copy this code. Pretty sure now it should be clear that how exactly are we storing the same. Great. So yeah, I think that's fine. Let us try to create a graph and see how it will fare. So let us create a graph like this. Let's say we have again 3 nodes, 1, 2, 3, and let us make it 4 only, or maybe we can use this one. Let me clear all this. We have 4 nodes here, right? So let us use this one, will be good. So graph equals graph adjacency list, graph dot add vertex A. Okay, minute, yeah. So we can add A, B, C and D. So these are the 4 vertices we have created, everyone. Now A is connected to B and D, D to B and B to C. Okay, so graph dot add edge. First I am adding an edge between A and B. Then I am adding an edge between A and D. Now I don't need to add B to A and D to A, that will be handled. Then next is B to D and B to C. So here what we can do, B to D and B to C. Great. So I hope all of you are able to understand. We have added just 4 vertices. Again, the code is very straightforward just on the basis of our discussion. I am just actually trying that all what we discuss, we are able to just code it down. And that's what coding should be. Nothing to remember. Okay. Now, what we can do here, we have added edge as well, graph.display. And let us run this. Great. So first it is saying that, okay, there are vertices A, B, C, D. Again, that is required. Although in this case, honestly, we can just be fine if we don't use it. I hope all of you understand why. Because when we add a vertex, we are adding this entry into my adjacency list as well. So I will never have a case like, for example, just to make it a little bit more straightforward, I can have E here as well. And let me just comment this line. Let us try to run this now. Minute. Yeah. See. So let us try to draw this, everyone. The very first thing you will notice, we have not missed out on any particular vertex, right? E is also there, though it's empty. Now, A is here. Then we have B. Then we have C. Then we have D. E we can keep anywhere else, should be fine. A is connected to B and D, as we can see here, A, B, and D. B is to A, B is to D, and B is to C. That should also be fine. C to B is already done. D to A done. D to B. So something like this of a graph is getting made, right? The weights are also there, and this is a undirected graph. Okay, bidirectional or undirected, because we see that if A to B is there, then B to A is also there. And I think yes, we are able to make our graph in a very nice way. So it is very much similar. A, D, B, A, D, B, and C is connected like this. Again, I have made an E so as to just show you that. In this, we can easily see this node where nothing is connected. Now, the benefit which we talked about, everyone, what is the benefit? If I want to find out if C is connected to A, what will I do? I will go to C. I will loop over this list and check if I am able to find A in this particular first one, right? So if I just do self.adjacency list of this C, then I will just find all the connections. So the good thing, if it is a overall very sparse graph, if it is, we are just storing the edges, right? If let's say no edges are there, this will all be empty, should be fine. I don't have to worry. But the best part, in O of n, I can just find out each and every node, okay? And if it is connected to other node, because I can just directly go and ask that node that, hey, if you are connected to this person or not. So I hope you get the idea that why this adjacency list is useful. Okay. So yeah, that was the major part, everyone. Now moving forward, we have to see one more implementation. The idea again is that can we again just make sure that we can optimize it little further? Maybe if we are good to use some space as well. Okay. So this is something kind of an approach which we used in many problem as well, right? We try to increase a little bit space and we make sure that we are able to somehow decrease the time complexity, and overall also that approach is pretty easy. So let's discuss that in the next video. But till now I'm pretty sure that you must have understood that what exactly is going in adjacency list and how that is different with your edge list, and why again adjacency list is overall preferred. The code is fabulous. The way we have written this code, honestly, you will not find it anywhere in even good implementation as well anywhere. So please make sure that you write this from scratch once at your end as well. Now you are a lot overall matured in terms of coding. We have done OOPS pretty nicely. We have done so many data structures. So after this video, I want all of you to even implement this part of code yourself as well. Okay.